Welcome to this explainer. Today, we're diving into a literal game changer straight out of Google research that is fundamentally reshaping how artificial intelligence reads. And I don't just mean reading short articles or quick emails. I mean everything from reading incredibly long books all the way to deciphering the very code of life itself.
So, let's kick things off with a deceptively simple question. Why do highly advanced AI networks absolutely struggle when you feed them massive walls of text? You'd think that with all the computing power we have today, an AI could just swallow a 500-page novel in one gulp. But the reality is, standard models hit a hard structural wall.
Well, to understand that limitation, we first have to look at the secret sauce behind modern AI, something called self-attention. Think of it like reading a complex mystery novel, where you have to cross-reference every single character's name with every other clue on the page. It is the engine driving the phenomenal success of state-of-the-art NLP models like Google's BERT. It works by connecting different parts of a text sequence together, allowing the network to understand the context of a word based on all the other words around it. It's brilliant, sure, but it comes with a massive hidden cost.
Section 1. The Transformer Memory Bottleneck and the Quadratic Curse.
Right, so here is the issue. Because standard self-attention requires every word to look at every other word, the memory it needs doesn't just grow in a straight linear line, it grows quadratically. If you double the length of a document, the computational cost doesn't just double, it quadruples. This quadratic curse makes it incredibly expensive, sometimes virtually impossible, to process long documents using standard transformer-based models.
Section 2. Enter BigBird, Google Research's breakthrough.
To tackle this, the researchers came up with a really elegant solution, a sparse attention mechanism they named BigBird. Instead of forcing every word to look at every single other word, which is what causes that massive memory explosion, BigBird is selective. It cuts the computational weight dramatically. But the true genius here is that it does all this without losing the theoretical power and capabilities of those heavy, full-attention models.
And the payoff for using this sparse attention? A factor of 8. Seriously, by alleviating that quadratic dependency using BigBird, standard computer hardware can suddenly handle text sequences up to 8 times longer than what was previously possible. That is a massive leap forward in how much context an AI can hold in its brain at any one given moment.
And because it can ingest all that extra context at once, BigBird effortlessly knocks it out of the park. When the researchers ran their experiments across long context NLP tasks, BigBird dramatically improved performance. What this means in practice is an AI that doesn't just scan a paragraph, but can actually comprehend an entire sprawling manual to answer complex questions or instantly summarize dense documents with absolute state-of-the-art accuracy.
Section 3. The 3 pillars of BigBird. Inside sparse attention.
So how does it actually pull this off? Well, BigBird's architecture is supported by 3 core structural pillars that work perfectly together to create this highly efficient network. Instead of one heavy, cumbersome mechanism, it divides the labor into global tokens, random keys, and local neighbors. Let's break these down real quick.
First up, we have a set of global tokens. You can think of these like an overarching overseer for the text. These global tokens attend to all parts of a sequence, ensuring that every piece of the document is being monitored and connected from a macro level. It essentially gives the AI the big picture.
Second, rather than a word looking at absolutely everything at once, each query is assigned a set of R randomly selected keys to attend to. By randomly sampling connections across the document, the network can stumble upon broad contextual clues and unexpected links, completely avoiding the crippling computational cost of looking at everything all the time.
Finally, BigBird uses a block of local neighbors labeled W. This guarantees that each node or word keeps a really strong grasp on its immediate surrounding structure. So you've got the global tokens looking at the big picture, the random keys making those unexpected leaps, and the local neighbors keeping track of the immediate sentence structure. Together, these 3 pillars satisfy all the known theoretical properties of full transformers, but run incredibly fast.
Section 4. Unlocking DNA with AI, beyond natural language.
Now, inspired by BigBird's newfound ability to handle these massive, continuous contexts, the researchers at Google asked a pretty radical question. What if the text sequence wasn't a book, but the biological code of life? DNA is, after all, just a very, very long sequence of information.
This led to a completely novel application.
The team took this AI, which, remember, was originally built to summarize documents and answer questions about language, and applied its attention-based model to extract contextual representations from vast genomic sequences, like DNA.
And the results? Honestly, they were remarkable. In their experiments, BigBird proved to be highly beneficial in processing these enormous biological inputs. Because it can look at a much longer stretch of the DNA sequence at once, it delivered significantly improved performance on highly complex downstream tasks. Specifically, it enhanced the prediction of promoter regions and chromatin profiles, tasks that absolutely require a deep, long-range understanding of the genetic code.
As we wrap up this explainer, I really want you to think about the immense possibilities this elegant structural shift opens up. By solving a fundamental math bottleneck, that quadratic curse we talked about, we've suddenly given AI a dramatically larger window to view the world. If AI can now efficiently map out giant text documents and decode the very blueprint of life with BigBird, what massive, complex sequence will it unravel next? Thanks for joining me on this deep dive, and definitely keep your eyes peeled on what these expanded sequence models do in the future.